heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, good evening, everyone, and welcome to Mount Washington Observatory Science in the Mountains lecture series. My name is Brian Fitzgerald, and I'm the Director of Science and Education for Mount Washington Observatory. Thanks so much for joining us this evening, and to tell us all about the observatory's new generation of pitot anemometers is weather observer and engineer Sam Robinson, who will join us in just a bit. Thanks again for joining the program. For those of you who are not already familiar, Mount Washington Observatory is a private nonprofit organization with a mission of advancing the understanding of the forces that create Earth's weather and climate. And we do that by operating our Summit Weather Station 24/7, 365, by delivering and offering educational programs, and by executing research and product testing on the Summit and beyond. Thanks again for joining us tonight. Excited for our speaker this evening and for tonight's topic. If you have any questions for our speaker this evening and you're joining via Zoom, make sure that you put your question down in the Q&A button, which you can find just down at the bottom of your Zoom toolbar there. We'll be able to collect questions throughout the entire program, and we'll be sure to save some time at the end. If you're joining us through Facebook, you can certainly ask questions through there. However, we won't be able to get to those in real time. We'll do our best to follow up afterwards, after the program. If you'd like to join us through Zoom for a future program, feel free to register for upcoming programs all over at mountwashington.org/SITM. Alrighty, well, I'm going to go ahead and launch a poll here before we get things going on this very special day. I should say happy Big Win Day to everyone out there. This day, 88 years ago, appropriately enough, Mount Washington Observatory, the fledgling organization, just in its second winter on Mount Washington, recorded a world record wind gust of 231 miles per hour. So very fitting and more than just coincidental that we are talking all about wind and anemometry this evening. And to get things going, including some anemometer related trivia, we have a poll that I just launched for those of you joining via Zoom. If you're joining that way, go ahead. We got 4 questions for you. We're curious where you're joining from this evening. Perhaps it's within a great state within New England. Perhaps you're outside of the region or even outside the country. Curious whether or not you have joined a Science in the Mountains program before. Yes, maybe it's the first program you've joined. No, maybe you've been joining along for, well, our long-running series here, our long-running monthly series. Thanks so much for coming back. And then a couple trivia questions from our speaker for this evening, from Sam himself. What's the highest wind gust that this next generation anemometer experienced during testing? Was it 154, 136, 171, or 231 miles per hour during testing? And we're going to be talking all about pitot tube technology this evening, as that is the primary piece of technology that this anemometer applies. And we're curious, where are pitot tubes most commonly used? Vacuum cleaners, aircraft, irrigation, or in manufacturing? Curious to see if people are familiar with this otherwise somewhat obscure piece of technology, unless you're really in the know there. All right, we'll leave it just a few more seconds here. I can see quite a few of you have already responded. Maybe just another few seconds here. And we'll go ahead and close it in 3, 2, 1. All righty. Thanks so much for participating. Great participation from New Hampshire, Massachusetts, and outside of the region as well, including we have 3 folks joining us from outside the US of A. Welcome everyone joining tonight. Is this your first Science in the Mountains program? Over 80% of you. Yes, you've joined before. Well, welcome back. Glad to have you again here with us. And then for the 20% of you, 22 of you this evening are First timers, welcome. Hope you'll enjoy this evening's program and join us for many, many more programs in upcoming months here. And then on to the trivia. What's the highest recorded wind gust that this new anemometer experienced during testing? Most of you thought 171 miles per hour. A good amount of you thought 231 as well, and mixed beyond that. And then finally, what's the most, typo here, most common use of pitot tube technology? My apologies, I was the one who typed that one out. 84% of you think it's in aircraft. All right, we'll have to learn from our speaker this evening to find the answers to those last two. All righty, well, at this time, I'd love to welcome weather observer and engineer Sam Robinson, joining us live from the summit of Mount Washington. He's on shift tonight. Sam, feel free to turn your camera on, turn your mic on. Can you hear me?
Yes, sir. I can hear you. Can you hear me?
Oh, yeah. And I got that lovely evening glow behind you in the weather room.
That's right. We're finally out of the clouds.
Oh, good for you. I'm sure it was a long shift. And I think you'll even show us some photo evidence of what you've been dealing with this week.
Definitely.
Well, Sam, feel free. Take it away. We'd love to hear all about the observatory's next generation of anemometer.
Awesome. Just going to share my screen. Let me know if you can see it.
Yeah, looks great. Go for it.
All righty. So hello, everyone. Thank you so much for joining my first ever Science in the Mountains program this evening. As Brian said, my name is Sam Robinson, and I'm a weather observer and engineer up here at the observatory. I'm currently on the summit in our main office, the weather room, and you may occasionally hear the wind gusts behind me, as it's all too fittingly very windy right now. I have been working here on the summit since July of 2020, so I've been calling the home of the world's worst weather home for almost 2 years now. I hail from West Townsend, Massachusetts, a little town in the northern part of Massachusetts on the southern New Hampshire border, and I graduated from the University of Massachusetts Lowell in spring of 2020 with a Bachelor's of Science in Mechanical Engineering. I came up here to the summit to experience the extreme weather, as well as to use my mechanical knowledge to help out with anything I could, and also to improve my understanding of meteorology, as it's a pretty strong passion of mine. So that's a little bit about myself. My engineering background is what brought me onto this project in the first place, as I truly wanted to grasp and understand everything about our newest anemometer that is in use up here on the summit. I'll start off here with a quick vocab word for everyone that I will be using many times during this presentation, and that is anemometer. For those of you who don't know, an anemometer is just a fancy word for an instrument used to measure the wind, more specifically the velocity or speed of the wind. I also include a picture diagram of our instrument tower here, which I'm sure most, if not all of you, have seen before. I will reference the instrument tower in our cold room many times during this program. The cold room is just the highest internal floor of the tower, where the majority of our electrical equipment for all those instruments safely resides. This anemometer project I will be talking about tonight did start a few years before I personally started working here up at the observatory, but I was able to get up to speed pretty quickly thanks to all my helpful coworkers and the information we have documented for it. As some of you may know, and as Brian mentioned, today is a very fitting day for a presentation on a wind instrument, as today is the 88th anniversary of our big wind day, the day we recorded our world record surface wind speed that is observed by man of 231 miles per hour. The summit of Mount Washington is a very windy place with an average yearly wind speed of 35 miles per hour. And I have come to learn that calm days, or even just any calm periods of time, are extremely few and far between up here. We constantly record wind data for our weather observations, as well as our long-standing climatological record, and it is crucial that we have the best instruments and systems obtaining that wind data for us. So before I get into the next generation anemometer project here, I did want to briefly touch on anemometer history up here on the summit. Measuring the wind has been something that has been done on the summit since the late 1800s, usually only during non-icy events though. It was quickly realized that such a unique location with such extreme weather required unique instrumentation. However, it was not until 1932 that our first heated anemometer was developed and utilized to measure the wind on the summit. So here are some of the early anemometers used on the summit. They were the standard 3-cup anemometers, which is on the right there, which are still used in some locations today as they're just simply tried and true. However, this style of anemometer does not handle icing well. Weather observers then began to use a bucket type anemometer, which is similar to the 3-cup in design, but it is able to be heated, so it does handle icing a bit better. The bucket type is pictured here on the left, and this anemometer is actually the heated number 2 that recorded the big wind of 231 miles per hour on this very day, 88 years ago. This style anemometer was utilized until 1945 when the first pitot static tube anemometer was developed by us here at the Mount Washington Observatory. So the timeline of pitot designs and developments, 1945 was the first pitot static tube attached to a vane to be used as an anemometer. The mask and skirt of this instrument were actually made out of a tin vegetable can, and it got the name the grandfather. According to an internal study done on the history of pitot tube anemometers here on the summit, this anemometer was used from 1946 all the way up until 1992. This instrument recorded all of the wind data solely to the haze chart, which you all may be familiar with, and we actually still have the same haze chart in operation today. However, it is now only used as a novelty way to visualize the changes in wind throughout the day, and also in emergency situations if our database was to go down. In 1990, a new pitot project was started to build a replacement for the grandfather pitot, and this project eventually yielded pitot 92, which went into use in, you guessed it, 1992. This was the first pitot tube anemometer used up here that utilized transducers and a data logger rather than solely just the haze chart. Transducer is another word I will be using a lot tonight, and it is basically just a sensor. So pressure transducer and pressure sensor are the same thing. It is worth mentioning that if you look closely at those pictures, the main aluminum body design of pitot 92 is strikingly similar to the body design for pitots 94, 97, 11, and 19. I was unable to get a definite answer, but I am willing to believe that this anemometer body design has been unchanged since 1992, or mostly unchanged. So why was there a need for a new anemometer design? Before this project came about, we of course already had wind measuring instruments, including a pitot tube anemometer already in use on the summit. So why did we need a new one? If something isn't broken, why should we try to fix it? Well, it's not that any of our instruments were broken. It's the fact that technology and instrumentation is always evolving and improving. We are using this wind data to help with our METAR surface weather observations to help keep the aviation community safe. And we also use this data to aid in forecast models as well as in our climate record. Of course, we want this data to be as accurate as possible. And as good as the current instruments were at the time of project commencement, there is always room for improvement. So I included this specific picture of a previous coworker's father flying over the summit in his Cessna airplane. And this is to represent the aviation community that we keep safe. But I also want you to notice the L-shaped metal tube on the edge of the wing. That's actually a pitot tube. And I want you to remember this aspect of the airplane for a future slide here in a few. So the real inspiration for this project was that the current anemometers in operation on the summit in 2015 when the project started were good instruments, but they were not great instruments. The RM Young, which you can see in that first picture, we actually still use today. It is a propeller-driven anemometer. It is very accurate for most wind conditions, including high winds, and also provides us with not only wind speed, but also direction, which is nice. The only problem with the RM Young is that it is unable to be heated. If we have icing or riming occurring, the instrument needs to be taken down due to prevent inaccurate wind speed data and eventually possible mechanical failure. The propeller begins to get iced up, which will slow down its rotational speed, which then provides falsely low wind speed data. Eventually, if we left it up, and believe me, tests and accidents have happened, the propeller and even the whole entire instrument can just disintegrate, and it's not cheap to replace. So they can usually handle light icing just fine, as you can see in that first picture, but not quite the extreme icing that usually occurs up here at the summit of Mount Washington. The other anemometer in use at the time in 2015 was a pitot tube anemometer, pitot 11. This anemometer is able to be heated, so it can handle most icing conditions. I say is, and can because pitot 11 is actually the same pitot tube anemometer that we currently have in use up here on the summit right now, which is pitot 19. At the time of the next gen project commencement, this instrument was referred to as pitot 11, but we are going to refer to it as pitot 19 from here on out in this presentation, as the instrument only underwent some very minor heater changes in 2019 to get that new name. As far as the anemometer itself goes, it is the exact same instrument. I figured it would also be important to mention that although it did get these heating system upgrades in 2019, the possible improvements that were initially determined for the next gen anemometer in 2015 had not been taken care of with that new 2019 version. Overall, the anemometers in use at the time got the job done, but were becoming outdated, and the improvements that could be implemented had become apparent over that time. So I will focus here specifically on the pitot 19 anemometer for a little bit, as the RM Young is not a custom in-house anemometer or one we can easily make changes to, such as adding heat. So first off, a little about pitot 19 and how a pitot-static anemometer works. In the early 18th century, French engineer Henri Pitot invented the pitot tube to measure fluid flow velocity, and then it was modernized to its current form by another French scientist, Henry Darcy, in the mid-19th century. The most basic explanation I can give of how a pitot-static tube works is that there are holes and tubes in the pitot tube, one at the end opening with an internal tube that's attached to it, which is the total pressure line, and then one or more holes on the side wall of the far end of the tube, perpendicular to the end opening, and those are also connected to another internal tube, which is the static pressure. So as air flows into that very end, the total pressure end, and also flows by the perpendicular static pressure holes, a difference in pressure is generated, which is called the differential pressure. This differential pressure can then be used to determine the velocity of the flowing fluid, which in our case is air. Its most common use nowadays is determining the airspeed of an aircraft. So remember how I pointed out that pitot tube on the wing of the Cessna a few slides back. They can usually be found on the wing, like in that picture, or on the nose of airplanes. The obvious difference between an airplane pitot tube and a pitot tube anemometer is that the plane is flying into the air, with the plane moving and the air being stationary. And with our anemometers, the anemometer is stationary and the wind is what's actually moving the air into it. So that's a little explanation on the science behind a pitot-static tube. You can also check out that little diagram I included. Our pitot 19 anemometer consists of the pitot-static tube, which internally contains the total pressure tube and the static pressure tubes. And that main pitot-static tube is connected to an aluminum body that has a vane, which helps point the instrument into the wind as it changes direction, and then the mounting post, which the body pivots on. So inside the body and mounting post runs the two lines from the total pressure and static pressure tubes that run down our instrument tower, almost 3 stories down to the office. These two lines, the total and static pressure lines, are then connected to the pressure transducers or sensors down in our weather wall, which then effectively determines that differential pressure and is able to convert it into an electrical current. That electrical current is then converted through a data logger, which also takes into account temperature and atmospheric pressure to the useful information that we want and need, which is the actual velocity or speed of the wind. So after years and years of using similar pitot anemometer designs here up at the summit, it slowly became evident that there were 3 big areas for improvement. So the first is the length of the tubing from the pitot tube on the anemometer to the pressure transducers where that pressure is actually measured. So the length of tubing in the pitot 19 system is super long. As I said, it travels 3 stories down from the top of the tower, and it exceeds 70 feet in length, which is 840 inches. So actually over 840 inches. It was theorized by Mount Washington Observatory employees back in 2013 that this very long length of tubing leads to dampening of pressure waves, which then leads to a loss of accuracy in the wind speed measurement. Basically, the pressure could be different at the transducer or sensor, than it is up at the actual anemometer itself. So along with possible dampening of pressure waves due to this excessive tubing length, changes in air density due to the changes in temperature is also a theorized issue. As the air travels down the tubes from the top of the tower to the weather room, it goes from outside, which is one temperature, into the cold room of the tower, usually a tad bit warmer than outside, and then eventually down into the weather room in the building itself, which is a much warmer setting. The pressure and thus wind speed is calculated off a set density of the air, but as some of you may know, the density of air changes with temperature. So along the same lines of tubing length comes the second area for improvement, which is ease of removal and installation of the instrument from the top of our instrument tower. The first 10 feet or so of pressure line coming out of that pitot tube itself is stiff copper tubing. After that 10-foot section of copper tubing, it then connects to plastic pneumatic tubing, which then carries it the rest of the way down. It is easy enough to disconnect the pneumatic lines from the copper tubing, but then you're still left with 10 feet of copper tubing from the anemometer that can't be disconnected when the instrument needs to be removed. It's also crucial during removal or installation that this section of copper tubing cannot be bent. This just means that extra care must be taken when the instrument is being removed or installed for maintenance or repairs, which then requires optimal weather conditions, many sets of hands, and very cautious movements. At the home of the world's worst weather, optimal weather conditions are a very rare occurrence. And even when they do occur, the availability of people to help, plus fitting everybody at the top of our instrument tower, is not an easy feat to coordinate. So the last big area of improvement is the heating system on pitot 19, which is basic and beginning to be outdated. The heaters were upgraded to higher wattage elements in 2019 when the name change occurred, but there was still plenty of room for improvement. In the worst of icing conditions, which are a pretty common occurrence during the middle of the winter, the heaters simply cannot keep up even when cranked up. I know from personal experience that sometimes it's required to go up to the top of the tower multiple times in an hour just to make sure that the instrument is clear of ice buildup. It usually takes a simple brush of a gloved hand to knock it off, but without that physical help, the instrument would ice up, and that eventually limits its rotational abilities to vane into the wind. In the worst cases, the icing may build up enough to partially or fully block those holes on the pitot tube, which then leads to erroneous pressure measurements and then therefore erroneous wind speed data. And a less common issue that can and has occurred is moisture or ice making it into the pressure system itself. So due to that heating system not being able to keep up and evaporating it quickly enough, which then leads to a clog. A clog leads to a heavily dampened pressure, which then leads to erroneously low calculated wind speeds, as well as a loss of gust sensitivity. That means that the wind gusts or sudden changes in the wind speed just get smoothed out in the data, making the wind speed look almost steady. Clogged pitot lines are one of the most dreaded occurrences for us weather observers, as it involves manually pumping the system, which can take a long time. And it also forces us to have to estimate the real wind speed for that clogged period. We estimate based off of the speeds that were being recorded before and after the clog, since during that clog period, the wind speed data is inaccurate. Another secondary downside to pitot 19's basic heating system that I wanted to mention is the controllers for the heaters, which you can see in that picture. They are manual controllers and are located up in the cold room of our instrument tower, 2 stories up from the weather room. So it's simply just an inconvenience versus a heating performance aspect, but when temperature settings need to be checked on or adjusted, it does require one of us to have to go up there to the cold room. So in order to address these 3 main areas of improvement, 3 main design improvements were decided for this next generation anemometer, which has been given the very fitting name of pitot 22. I will reference it as pitot 22 from here on out, just to keep things simple. The 3 main design improvements chosen for pitot 22 were minimized tubing length between the pitot tube and the pressure sensors reading the pressure, no unbendable long copper tubing section, and then also a more robust heating system with remote control of the heat settings. So in theory, how would these help us? So it may be somewhat self-explanatory at this point, and I hope it is after the last few slides, but these design improvements that I just mentioned would then provide us with an anemometer that has greater accuracy, greater sensitivity, and therefore more accurate wind speed data due to the minimized tubing length. An anemometer that is easier to remove or install from our instrument tower when maintenance, repair, or calibration and testing is needed due to that loss of that unbendable copper tube section. And then also an anemometer that can handle extreme icing conditions, requiring minimal manual de-icing by us observers, which keeps us safe and also able to spend more of our time working on other tasks. So now I'm going to talk about the development of pitot 22. So the project really came to be thanks to a collaboration with University of Massachusetts Lowell and the company General Electric, or GE, based out of Lynn, Massachusetts. The director of research for Mount Washington Observatory at the time, Dr. Eric Kelsey, applied for funding through the General Electric Volunteers Program. GE employees at the time, Michael Gagnon and Peter Rock, built internal support in their company, and they also got fellow employees Edward Walton and Matthew Thomas to also volunteer their time, all of whom contributed to this project. And then they also brought on a fifth employee, Joe Chavez, also came onto the project in 2018 for his electrical expertise. Besides personnel, the GE Volunteers Program also provided $16,650 in funding for parts and supplies. UMass Lowell engineering professor Dr. Sammy Sheena then recruited senior mechanical engineering students for 2 years of the project, which was 15 to 16 and 16 to 17. And I'd like to just take a quick second to thank all of them, as we would have not been able to make this project happen without them. So we're getting into the more technical aspects of the project now. I will try my best to explain as well as I possibly can, but do remember, if you have any questions, feel free to drop them in the chat and I will try to answer them at the end of the presentation. So the design for pitot 22 is a fully custom, all new design, but the general idea used were all similar to previous pitot tube anemometer designs, even all the way back to our first in 1945. Like all pitot tube anemometers, it was a given that this one would have a pitot static tube attached to a rotating metal body with a tail vane that's going to help keep it pointed into the wind as the direction changes. Pitot 22 features an anodized aluminum body and vane, which is a lightweight but strong metal. The vane is shaped to a standard NACA 0018 airfoil design, and that was just basically the one that was found to be the best fit for this application. This style tail vane allows the anemometer to align within 15 degrees of the actual wind direction at speeds of 25 to 35 miles per hour, with the misalignment value going down as winds go up. So for reference, it is theorized that up to a 20-degree misalignment will have almost no impact on measured wind speed, so that this 15-degree misalignment was in spec. The body of the anemometer is specifically shaped and size so that the pressure tubing and transducers are able to fit within it, because remember, we were trying to minimize tubing length from pitot tube to transducer or sensor. The anemometer body also has to swivel in order for it to properly vane and rotate into the wind direction as the wind direction varies. So it's fitted with a bearing so that it can freely rotate. And then of course, the heating system is a fully new upgraded design to previous versions that were built by us. UML student Brandon Honeycutt, who was also an employee of FMC Technologies, was able to assist by providing us an IQ4E controller, which is built by FMC, as well as their proprietary software, which we were provided with a free license. So special thanks to him and them as well. So now we're going to be jumping into even greater detail here. Here are some of the more important design details really targeted at those three main improvements that we were looking to achieve. So first off is the use of two pressure transducers, a 0 to 10 inch pressure transducer and a 0 to 7 inch pressure transducer made by the company Omega Incorporated. This isn't necessarily unique to pitot 22. We also utilize two different transducers in pitot 19 system, but it's important because with pressure transducers, it's not just one size fits all speed ranges. We utilize the 0 to 10 for lower speeds, with its range going all the way up to 156.4 miles per hour. And then the 0 to 70 is for higher speeds, and its range goes all the way up to 417.9, so 418 miles per hour. Although that 0 to 10 would be suitable for most winds that we experience up here, with that range, it does begin to lose accuracy the closer it gets to that end value. And plus, we want to capture potential record-breaking wind speeds, which is where that 0 to 70 comes in handy. Having two pressure transducers also provides us redundancy in the event that one of them fails. So thanks to that larger size of Pito's 22 body and tail vane, both transducers and the pressure tubing is able to fit inside, which truly does minimize that length of the pressure lines. You can see that in that first diagram there. The transducers, which convert the pressure reading to an electrical current, then simply just uses electrical wires to send the data down through our instrument tower to a Campbell Scientific CR6 data logger, which is located in the cold room of our tower, which then converts that voltage to our wind speed data. So that new heating system that I touched on a little bit ago is also an important feature, as we were looking to build this anemometer with the most robust heating system possible. It does use a lot of power when it is cranked up, but it certainly does get toasty. The controller for the heaters from FMC Technologies is located up in our cold room of the instrument tower, and that is similar to Pitot 19, but the difference is this controller is connected to our network, so it can be remotely monitored and controlled. So how is it an improved design, and how do these incorporated features actually benefit us? So I may be repeating myself a little bit here from those earlier sections, but those were more along the lines of our initial goals for improvement, and this is how we were actually able to achieve those goals more specifically. So starting with the minimized length of the pressure lines, both the static and total pressure lines are about 6 inches in length, and that's quite a big difference compared to the 840 plus inches that are in Pitot 19 system. The pneumatic tubing and pressure transducers are fit right into the body of Pitot 22. This helps us in a few different ways, and it actually helps take care of our two main areas for improvement, which is the tubing length and ease of removal installation. With a self-contained pressure system, we're keeping that total system volume much, much lower, which in turn helps keep that pressure dampening I previously touched on to an absolute minimum. With everything being self-contained in the body of the anemometer, we are also effectively eliminating any temperature changes like the long tubing length of Pitot 19 was subjected to. So these specific improvements do lead to more accurate pressure readings, which then equals a more accurate wind speed data. Along with that improved accuracy, we achieved greater sensitivity of wind speed fluctuations, which also equals more accurate wind gust data. So as you might be able to guess, this feature also eliminated that long unbendable section of copper tubing and simply just replaced it with electrical wires. So these wires have connections down in the cold room that simply just have to be unplugged if that instrument needs to come down, making for a much easier removal and installation process when need be. This instrument does weigh quite a bit, so it still requires a few sets of hands, but the whole process usually is much quicker and smoother, and it definitely requires less precision and worrying about just damaging any parts of the system. I do know from experience that this thing is pretty burly, pretty heavy, but it's a worthwhile trade-off for a robust design that accomplishes those goals we were trying to achieve. So the incorporation of the new, more robust heating system in Pitot 22 has definitely been an improvement over Pitot 19's basic system, with the heaters contained within the aluminum construction of the body, even down the skirt and mounting portion, as opposed to just heat tape simply being wrapped around the mounting post like it is on Pitot 19. This better integrated heating system helps to keep our instrument almost completely ice-free in even the harshest conditions. I say almost because in rare cases, we do still have to go up and knock some ice off, but it usually only requires a slight vibration of the mounting post to knock off any of that accreted rime or glaze ice. In my experience with major icing events, I'm not really sure there's any heating system in existence that could realistically keep up. It does definitely get really crazy at times. And relative to Pitot 19 and our other previous anemometers, though, it definitely performs much better. The controllers for the heating system are wired into the cold room of the instrument tower, and they're also linked to our network. So that allows for remote control and monitoring of those settings. As I previously mentioned, Pitot 19 requires that manual control, which means us weather observers have to physically go up there to change or monitor those settings. So now we're going to look at a little timeline of the development for Pitot 22. So basically, just in 2013 was when we had the initial idea and when the planning stage kind of started. And then the project was officially commenced in 2015. The design stage took place between 2015 and 2017. Manufacturing and assembly was in 2017, as well as initial wind tunnel testing. And then we initially installed it on the summit in 2018. The operation in comparison to other anemometers started in 2018 and is still going on right now. And then we did have to do some modifications and upgrades and repairs, which I'll get into in a little bit. And it basically came down once a year since going up just to get some maintenance. And then we have had some third-party testing done on this instrument it started in late of 2021 and it's gone until early 2022. We do now have the instrument back on the summit. So the idea to improve our pitot tube anemometer system was in the works well before the actual project commencement. Back in 2013, students from UMass Lowell studied pitot 19 system and determined that that excessive tubing length did in fact affect the system. Their suggestion was to move the transducers up to the cold room. This would decrease the system volume, but it did not take care of the other areas of improvement. And it would also lead to a loss of our haze chart, since the haze chart operates directly off those pneumatic pressure lines. And it became apparent that it was time for an all-new pitot anemometer design, as opposed to just simply continuing to upgrade old designs, considering that that basic design and physical build was relatively unchanged since 1992. The opportunity for a multi-organization collaboration was realized with discovery of that GE Volunteers program and its connection with UMass Lowell's engineering department, specifically their design, build, test capstone project, which I actually had to do one of those as well. This project replaces aging measurement equipment, and it also does try to incorporate regional organizations and businesses. So basically, it was useful for all involved as it provided the observatory with the needed funding and assistance. It also provided UMass Lowell students with an informative opportunity to help the science community through that project. And then it also helped General Electric with community benefits and relations. And then, as I had mentioned previously, in 2014, the director of research at the time for the Mount Washington Observatory, Dr. Eric Kelsey, among other Mount Washington Observatory IT specialists and weather observers, they all came up with a project plan, including design constraints and optimized specifications, estimated costs, and a rough schedule. And then the next gen anemometer project was officially commenced in October of 2015. So the design stage took place between 2015 and 2017 with help from all involved using our design constraints, our sizing calculations, budget, and important improvements over those previous pitot anemometer designs. The technical drawings and physical design model were produced using the computer-aided design program SolidWorks, which also provided a platform to perform some preliminary testing of the design before it was even actually physically manufactured. So General Electric and UMass Lowell provided their facilities to machine, build, and test this new anemometer design. The exterior aluminum parts of the anemometer body were anodized at TNT anodizing in Lowell, Massachusetts. And that's just for some added durability to survive our harsh environment that is the summit of Mount Washington. So thanks to in-program testing with SolidWorks, the computer model of pitot 22 was able to undergo some basic initial testing to make sure there were no glaring issues right off the bat. Mechanical engineering students at UMass Lowell ran a bunch of theoretical tests to just ensure that the design would be robust enough to handle our harsh conditions, as well as some extreme record-breaking cases as well. I'm not going to go into technical detail here, but all the tests confirmed that it could handle the world's worst weather, and it was found that the design did not need any changes in dimension nor material selection. The anemometer was also initially tested in the UMass Lowell wind tunnel after its manufacturing, just to confirm proper operation in real wind. So then pitot 22 was first installed up on the summit on August 18th of 2018. And as with almost all new products in existence, the real world testing is what really matters. So you can test all you want on a computer program or in a lab, but the real performance of a product only shines in its intended environment of use. So real world testing is going to show you, how well the theoretical design, the computer design, and then that manufactured design actually match up. There were a few small specific areas for improvement that were realized right off the bat, and pitot 22 did come back down off the instrument tower in September of 2018 due to some odd behavior in the 0 to 10 transducer. We just sent it back to the manufacturer for inspection, and they were able to recalibrate it, and as well as change the threading on one of the ports just to match the other transducer. So it just had a mismatch thread. And then it was also realized that the orientation of the transducer inside that tail fin was an important aspect to its performance. So our IT director, Keith Garrett, then 3D printed a plastic holder to keep them in the correct orientation. So the Mount Washington Observatory crew was then able to get it back from get that pressure transducer back, and was able to reinstall everything into the anemometer and reinstall it on the summit on February 23rd of 2019. And that was just in time to measure the 171 mile per hour gust on February 25th of 2019, which was actually a new record for the month. And it's important to note that pitot 19 also recorded a gust of 171 at the same moment, which was definitely a good sign for the initial integrity of this new pitot. So here's a quick video I wanted to show just of a past observer de-icing the instruments in high winds. I actually was doing the same thing up here for a good part of today. I believe this is actually the morning after the 171 event. The winds still do look to be pretty elevated here though, probably up around 100 miles per hour. You do have to look closely to see pitot 22. If you blink, you might miss it, but the camera does briefly pan over it at the beginning here, and it's the instrument closest to us. And unsurprisingly, in the video, it's looking pretty ice-free. So I do have to warn everyone, the audio might be a bit loud on your end, depending on how loud your volume is, but I'm going to try to set it here at a good volume before hitting play. So in the summer of 2019, a few months after that 171 event, the pitot did come back down from the instrument tower for some more small modifications. A few internal parts were upgraded to help improve the performance and durability of this instrument. An internal water issue was figured out with the slip ring, which is pictured in these pictures here, and it was resolved, as well as upgrading the pneumatic tubing and connectors at the same time. And this actually allowed for even less tubing in the body of the anemometer and a better fit for everything inside the tail fin. So in a nutshell, this basically just shows that while initial testing is super important and it can be helpful, real world testing is the most important. We were able to resolve these initial issues while also improving the design even further than originally designed and manufactured. So it was definitely a win-win. So most recently, we actually sent pitot 22 off to the University of New Hampshire for third-party wind tunnel testing. And this was done as part of the instrument's journey to becoming an operational anemometer for us up here, as we want to make sure that this instrument's recording the most accurate data as possible. So remember, our wind data is sent to the National Weather Service in our METAR reports for aviation purposes. And it's also sent to them for forecast model input, and it also goes into our own climate record. So the more accurate this data is, the better it is for all three. Along with the physical anemometer itself, we also sent them some recorded wind data from some of our most notable wind events so that it could be analyzed and compared to our other anemometers that were also in operation, recording data at that same time. So before any wind tunnel tests were performed on pitot 22, a simple calibration test was run to verify proper operation of those pressure transducers at the anemometer's new off-summit location. And it was found that these two transducers both exhibited less than 0.7% of uncertainty in pressure measurements. So although the wind speed is not solely just calculated off these pressure measurements, for reference, the World Meteorological Organization requires a 10% accuracy or uncertainty for wind measurements. And then taking a look at these figures for each sensor, it is the known input pressure of the calibration tool plotted against the actual pressure measurement that was determined by the sensor, so the actual output. And you should notice that a visual difference is basically impossible to see, but it's the 0 to 10 sensor on the left, 0 to 70 on the right, and the difference is so minimal, you can barely even tell. Also, before wind tunnel testing, a mounting angle calibration was performed, just to confirm that an orientation offset does apply to this type of pressure transducer. Basically, the orientation or angle of the pressure transducer plays a role in the measurement of the pressure. So in operation, we apply a correction factor for the angle at which they're oriented inside the body. And this lab test just simply confirms that the correction factor does in fact play a role in the accuracy. The first performance test done with pitot 22 was a balloon pop test, which was used to simulate a wind gust. And this is done by providing a very quick increase in pressure, Since the new design was supposed to be more sensitive to wind gusts, we wanted to determine how quickly the pressure transducers respond to sudden pressure changes. And it was found that a great way to do this was to just pop a balloon at the end of the pitot tube and then simply study the instrument's response. So in more technical terms, it is desirable to determine the transducer's transient response characteristics. And then this balloon pop test is basically going to provide that needed input to produce this. And it was found that the sensors do experience a little bit of overshoot and oscillation before they eventually damp out to a steady measurement. So there's a little bit of resonance there through a series of very technical formulas and extensive calculations. It was found that the settling time for the 0 to 10 transducer was 69 milliseconds, and then 56 milliseconds for the 0 to 70 inch transducer. And the overshoot percentage was found to be 144% for the 0 to 10, and then 153% for the 0 to 70. So I'm sure some of you or most of you may be wondering, okay, what does all this mean in terms of the accuracy and performance of the actual instrument? The engineers at UNH explained to us that the step input from the balloon pop provided a measure of the worst case overshoot. And in the real world and in practice, wind speeds should not change so suddenly. And this just means that the diaphragm of the pressure sensor would not experience such a sharp acceleration and therefore would not overshoot. And they also explained to us that the settling time is much shorter than our 1 second average wind speed that we record, and then also the 200 millisecond sample period that we currently use. So therefore, this underdamped nature of the sensors will likely not produce error in the reported average data. In other words, these characteristics of the omega pressure transducers are not of concern to wind gust accuracy. So after these initial calibration and response tests were completed, pitot 22 was then installed into their wind tunnel at the on-campus John Olson Advanced Manufacturing Center. And you can see in that picture, it's tucked in there in the wind tunnel. The UNH pitot tube was connected to a vertical manometer as well as a factory calibrated Cetra 0 to 10 pressure transducer, which we provided them with. So basically we put our instrument in there and it was installed in tandem with their wind tunnel reference pitot. And it was positioned in a way that would subject the stagnation ports of each tube to similar conditions. And it should be known that while we were trying to simulate real wind experiences as closely as we possibly could, it is nearly impossible to do so in a lab setting. And at the end of the day, each anemometer is expected to read slightly different, as these are all different instruments and they're all unique in their own way. The wind tunnel was operated at a range of 0 to 130 miles per hour. And then we recorded that wind speed data through both pitot tubes. And I just also wanted to mention that this is just not an easy test to make happen by any means. So some difficulties were expected and did occur. So taking a look at the results in the left figure, figure 8, the first thing that sticks out is the manometer readings, which is the green plus sign, and they were not being consistent with the other devices that were inside the wind tunnel. And it was later found that the cause of this was just a pinch in the manometer tubing, which was fixed for the following tests. And you can see that the two sensors from pitot 22, both 0 to 10 and 0 to 70, provided very similar pressure readings throughout the duration of the whole test, which was definitely a good sign. And also somewhat expected, as these wind speeds were within both of those sensors ranges. The pressure sensor from the wind tunnel reference pitot did read slightly different pressures toward the high end of the wind speed range. But again, the trend is more or less what we were looking for, as these are all different sensors and the difference is marginal. Taking a look at the right figure, figure 9, that's actually recorded wind speed data over the course of the test. And if you look closely, the two sensors from pitot 22, red and blue lines, they clearly read lower than the wind tunnel reference pitot cetra sensor, which is that yellow line on the graph. The tunnel reference sensor read 3 miles per hour higher than our pitot 22 at the point of the test where the maximum difference occurred. And the engineers at UNH then speculated that there was possibly a physical flaw in the cetra system, such as maybe a leak in the tubing, especially since the difference towards the high end of the speed test was proportional to that difference in pressure readings that I just discussed and that you can see in figure 8. So to verify that the reference pitot cetra sensor was well calibrated, they tested it with that same calibration tool that we used for that very first initial test on pitot 22 sensors. And only a minimal difference was found between the outputs of the reference pitot and pitot 22, which can be seen in this figure here, figure 10. The data plotted here is pressure reading over the course of that test time. The data between the two is actually so close, it's hard to tell even where they differ. If you look at 56 seconds and 56.18 and 57.38, you can slightly see a little bit of red underneath the gray, but it's really hard to tell where they differ. And since this reference pressure sensor was not found to be faulty, then some further investigation focused on the physical setup in the wind tunnel. So it was decided that due to this 3 miles per hour maximum difference, it would be useful to obtain a third data set to further compare the wind speed. We provided the UNH testing team with an anemometer that's actually not a pitot anemometer, but it's an ultrasonic type. An FT Tech ultrasonic anemometer was then installed and the same test was run again. This figure here, figure 11, shows a comparison of all three anemometers, with the wind tunnel reference pitot again reading 3 miles per hour higher than our other anemometer, which this time was the FT Tech. I did think it was interesting to see that while the maximum difference of 3 miles per hour was the same for both tests, so both the pitot 22 test and the FT Tech test, which were performed completely separately, they both showed a maximum difference of 3 miles per hour to the reference pitot. It's kind of odd that the maximum speed measured by the wind tunnel reference pitot was actually about 10 miles per hour higher in the test with our FT Tech ultrasonic compared to the test with our pitot 22. And this is at the exact same RPM setting for the blower in the wind tunnel. A collective theory was that the physical size of the anemometers in the wind tunnel may have played a role here, as the body of pitot 22 is much larger than the size of the FT Tech. It's also pretty clear that the difference in wind speed between instruments across the board increases as that wind speed increased. At lower speeds, all of the instruments read relatively close to one another. I want to stress again that this is actually not as negative as it may seem, as all these instruments are different in design and some difference is expected, especially at wind speed, as wind speed is increased and the 0 to 10 sensors approach those upper limits. This is also the main reason behind that 10% allowable difference, which is set by the World Meteorological Organization. And then final testing, or analyzation rather, was done on real wind data sets that we at the observatory provided the UNH engineering team with. And one of the notable data sets is shown here, which is that February 25th of 2019, the same day that recorded the 171 mile per hour record gust. So this set was chosen as the wind was elevated for that entire day with multiple gusts over 100 miles per hour. The UNH team found that an average difference of 4.1 miles per hour existed between the 0 to 70 sensor in pitot 19 and the 0 to 70 sensor in pitot 22 for the period of 6 p.m. To 8 p.m. Eastern Standard Time, where winds were in the range of 90 to 160 miles per hour. And if you notice, it's in 24-hour time there. So it's between the period of 1800 hours and 2000 hours. I did some investigating myself, and the average wind speed for this period of time was 136 miles an hour. So an average difference of 4.1 is only a 3% difference, which is well within those requirements set in place by the World Meteorological Organization. And multiple other data sets were analyzed, varying from low wind days up to high wind gusty days. The UNH team found that overall at speeds of 30 to 120 miles per hour, the 0 to 70 omega transducer in pitot 22 and that 0 to 70 cetra transducer in pitot 19 correlate extremely well. And they're actually within a 1 mile per hour difference. Above 120 miles per hour, the difference between the sensors does appear more significant, but it does still remain within that 3%. On average, pitot 22 reads about 2 miles per hour lower than pitot 19. With all this being said, it must not be forgotten that the whole point of developing pitot 22 was for improved accuracy. And in these past real wind data scenarios, we're using pitot 19 as the reference. So to determine which anemometer was actually more accurate in these historical scenarios would be pretty close to impossible at this time, especially in a controlled lab setting. It could be potentially theorized that by now testing the pitot 19 system in a similar way, we could figure that out. But unfortunately, at this point in time, pitot 19 and its entire pressure system have now aged over 3 years. So as we continue to improve our instrumentation up here on the summit, we are already looking ahead to possible improvements we could make to pitot 22. Some ideas that we've discussed are adding wind direction measuring capabilities, as our winter wind vane is now starting to show some age and wear as well. Another idea is a digital haze chart from pitot 22's database, in case we do end up removing pitot 19 and we lose the actual haze chart function. And we do know that everyone enjoys seeing that visual representation of the wind during those big events, so that would be nice. We also would like to install some sort of anemometer on our southeast side of the summit, as winds that come from the southeast have to travel all the way across the summit cone to get to our instruments on the northwest side. Our prevailing winds are usually out of the west and northwest, so the current location of the instrument tower is ideal. However, it would be nice to have an alternate instrument for those odd southeast wind events. So at this point in time, we are pretty satisfied with the performance of the next generation anemometer, pitot 22, and we look forward to finishing up the final stages of this instrument becoming our primary pitot tube anemometer up here on the summit. We're planning on continuing to run it alongside our other anemometers to further compare its performance and also to finalize any last minute changes to the instrument that we might need to make in order for it to be as accurate as possible. We do hope to have it set as our primary instrument this spring after finishing up our internal report on it and then getting approval from the National Weather Service. And you can see that picture I actually took just from the other day. We had a pretty significant glaze icing event up here, but as the picture shows, the picture doesn't lie. Pitot 22 is standing proud there. No ice. So I'll finish here by saying that Mount Washington is truly the home of the world's worst weather, with extreme conditions that do necessitate custom anemometers, which are high winds, extreme cold temperatures and icing, and also heavy precipitation. Here at the Mount Washington Observatory, we have a long history of custom-built anemometry with significant support from those outside partners, and we have relied on pitot tube as the primary technology since 1946. This next generation anemometer, pitot 22, represents significant improvements in physical construction, ease of removal and installation, as well as heating power. If you visit the summit over the next few months, be sure to take a look up at the top of our tower to admire its shiny and sleek aluminum figure. That's all I have for now. I hope you enjoyed the presentation. I certainly enjoyed presenting it. And I believe Brian will now join me for any questions that may have been asked.
Yeah, all right. Hey, Sam, that was excellent. Thanks so much. I know we've been talking a lot in preparation for this, but excited just how much shows how much time you've put into all of this. A lot of different people that I know you pointed out this evening already that have contributed to this project over time. So thank you for acknowledging them, and lots of other staff here at the observatory, but certainly a lot of outside partners who've helped support this project. Would love to welcome any and all questions. We've gotten a ton of really thoughtful questions in the Q&A on Zoom. So again, feel free to submit your questions using the Q&A button that you can find on the toolbar there. We'll try and get to as many as possible, but as you can see, Sam did put up the email there, research at mountwashington.org or education@mountwashington.org, whatever you'd like to use to get in touch with us or leave a question on Facebook. We love talking about these things and answering questions, so by all means, bring them on. And let's just get to as many as we can. Sam, question for Kevin. How many cups do you know are on that bucket style anemometer, like the heated number 2? Do you happen to know off the top of your head?
Don't. I want to say 6 or 8, but I'm not positive off the top of my head.
Yeah,
I
well,
think we actually have that instrument up here in the museum.
we sure do. I was going to say, Kevin, come on up to the Summit Museum. You can see the heated number 2 in all of its glory in the Extreme Mount Washington Museum, and we can count those cups with you there. Great question here from Rick. I was curious about pitot tube anemometers in general and whether or not they would work well at lower altitudes as well, not just, specific to the top of Mount Washington or even higher.
Yeah, honestly, I think the best way to answer that question is with our experience up here, we usually rely on our RM Young for lower wind speeds. And I know that lower elevations tend to experience lower wind speeds in general. So usually we put our RM Young up, even if we are lightly icing, when we get down below around 20 miles per hour. And as most of you probably know, down at low elevation, 20 miles per hour can actually be pretty significant. So I would say maybe like on the coast where higher winds are usually experienced more often, they'd be a good use, or in places sort of similar to us, so like higher elevation of low elevation, where those higher wind gusts can reach down. But usually at lower elevation, the regular old propeller driven anemometers is the best, just because those wind speeds don't get high enough.
Yeah, I guess you'd really need a lightweight body to be able to vane into those winds at those low speeds. And, yeah, fewer challenges down there, I guess, in general that
Yeah, definitely.
don't necessitate a pitot. Interesting. Okay. A few people asked this, including Doug was curious. I know you kind of referenced it in the testing, but, so the pitot tube itself, it's on, a perpendicular post, but the pitot itself is pointed downward. What's up with that?
Yeah, so up here on the top of a mountain, that wind has to force itself up over the topography of the mountain. So it was actually a calculated value. They studied it and figured it out that a 7-degree attack angle from horizontal, 7 degrees down, is the most accurate. And that just helps us with those winds that are being forced up and over. We might possibly miss wind if we had it perfectly horizontal, just because that wind kind of has a bit of an angle to it itself as it's being forced up and over the mountain. So yeah, I didn't really touch on that, but 7-degree attack angle is what we go with up here.
Right. Yeah. So definitely it's been built into other anemometers over time. Clearly. Yeah. That's right. Wind, the mountain creating its own wind, certainly just with the shape of the mountain itself. So taking that into account. Good question from Sandy about anticipated lifespan of pitot 22. I don't know if, I haven't had this conversation with anyone. Have you thought about this? Have you seen any info on this?
I mean, so just comparing it to pitot 19, I think the body and just the physical build of it seems much more robust. So I would like to think that it definitely has a longer lifespan than that older pitot design. Obviously, we have no real way of knowing. It's definitely going to depend on weather conditions and icing and all that. But yeah, I'd like to think that this design is definitely more burly and probably will have a longer lifespan than those previous designs.
Yeah, and I don't think it's a set it and forget it situation. Obviously, all of you up there need to still take care of that instrument and who knows, the little bits of maintenance that'll need to take place, which reminds me, I kind of had to cheat on this. I've been asking off screen here our director of technology, Keith Garrett, who has been instrumental, sorry for the pun there, in helping with this sensor, and certainly knows quite a bit, just like Sam, and was curious about a question that we received, and apologies, I forget the name here, about the bearings. The bearings need to be lubricated on this instrument. What do you know about the bearings? Because I had to ask Keith about this, and I can back up just in case you don't have info on that.
So I don't know for sure, but based on my experience with bearings in general, I would like to think that the bearing is pre-lubricated. So it's probably packed with grease when it's installed, when it's new. And I'd like to think that usually for the life of a bearing, that internally packed grease usually takes care of it. But I don't know. Definitely would love some help here.
Yeah, sure. Well, again, I did not know this off the top of my head. I had to ask Keith, and because and excuse me, it's a question from Chuck who'd asked, because also curious about how extreme temperatures might affect that lubrication or the grease that's in there. Well, this was a design consideration, and in fact, it uses ceramic bearings. So I guess no lubrication in there specifically to try and combat those temperature extremes. But like all bearings, all things with friction, eventually things, I guess, wear down. So I bet that'll be one of those pieces that down the road needs a little bit of maintenance.
And the other thing would be that with the body of it being heated, grease doesn't usually like heat. It usually thins out. So that does make sense. Yeah, ceramic bearing is definitely going to hold its properties through a wider range of temps.
Sure. Here's a great question from David. I was curious, what was the maximum wind that was used in the wind tunnel test at UMass? And I guess I'll even expand on that a little bit, maybe. What are the maximum wind speeds that we got to test at UMass Lowell and at UNH, if you know off the top of your head? Because I know it's not the same as what we got to test in the real world.
Yeah, I think so. I'd like to assume that UMass Lowell may have been a bit higher. So at UNH, it was around 130 miles per hour. I think the actual real measured wind speed there in that graph was 136 or 132. But I do know just physical sizing, the wind tunnel at UMass Lowell is much larger. So I'd assume that it possibly could have been tested at a higher speed, but I don't know for sure.
Yeah, and certainly I'll put the plug out there now. If anyone knows of wind tunnels that they'll let us turn the wind speeds above, say, the 150 that we got to do at UMass Lowell, let us know, because theoretically, as you mentioned earlier in the presentation, this sensor can measure much higher wind speeds. Excellent. Lots of really great questions here. I forget I've already passed the question here. I know someone asked sort of generally any implications potentially for the aviation community. Do you think, I'm not sure, what interest maybe aviation engineers, aerospace engineers may have in the knowledge from us. I know oftentimes we're kind of trying to borrow from the knowledge of aerospace engineers for our applications. Anything you can see being beneficial to them?
The only thing I could think of off the top of my head is possibly just the response of our pitot system compared to the use of a pitot system on an aircraft. So there may be some differences that could be noticed, the way we use the pitot system versus the way it's used on an aircraft. That's the only thing that really comes to mind. I'd assume there might be some slight difference, but I think the technology is pretty much the same. So yeah, like you said, I think we're basically using it from them.
Yeah, it'd be good to know, how they heat their instruments. Certainly, they don't want pitot clogs happening on those all important airspeed indicators and things like that.
Very true. Yeah, I'd assume the heaters are that's probably a similar technology to what we use up here on the pitot tube.
Oh, interesting. Yeah, question here from former observer Mike Dorfman stating, I noticed the external wiring, that small little box that's on the outside of the mast of the pitot. Is that for heating? Power for heating?
Oh, I'd need some help from Keith there.
Oh, all right. I already see Keith typing in my chat, letting me know. I've already forgotten how that one got added on here. Oh, we'll get an answer there. All right, I'm already getting the answer from Keith. Thank you, Keith. Thermocouple for measuring the mast temperature. So we want to measure in order to know, what to change the heaters up to. I guess we probably need to know what the current temperature of those surfaces are, huh?
That does make sense.
Like we do with the Pitot 19 as well.
Yep.
Lots of kudos out here from folks, both to UMass Lowell. I know a number of folks from UMass Lowell, General Electric, joining us tonight. Thank you so much for everything you've all done to help us get to this point. Some good question here from Gardner. Do you have any difficulty with maintenance issues for Pitot 19? Obviously, Pitot 19, current instrument still the gold standard data. I think you've referenced a little bit about this, but what are some of those maintenance challenges that are faced with Pitot 19?
Yeah. So I mean, at this point, we only take it down if definitely necessary. So in my experience up here, we have had to take it down one time for some heating repairs. One of the heaters burnt out and we noticed it was starting to ice up during those heavy icing events. So we did have to remove it for that. But with that instrument, we usually just leave it for, if it needs to come down, we will take it down. As far as performance goes, generally across its wind speed range and what it's been measuring over the past few years, when the RM Young is up as a comparison instrument, it's been matching pretty much exactly to the RM Young in those optimal conditions. So we don't necessarily have a reason to take it down as far as performance goes yet, but definitely we're definitely going to look into studying it and seeing if its accuracy or its performance has gone down over these past few years. So that would be interesting for the future. But yeah, no, we try to leave it up there.
Yeah, yeah, interesting. And I'm curious. Question from Hank about heating. Do you know off the top of your head, or maybe you have this figure nearby, maximum heating wattage on this new instrument? Keith, I'm sure will scare you an answer.
Oh,
Oh my gosh, he's fast.
he gave me
3,800. I'm sorry. That's not even fair to ask you a question and not let you answer.
have him give you the equivalent. I think he recently told me the equivalent. It's like running like a certain amount of microwaves all at once, or it's crazy. The amount of power it's using is quite high, but we need it. Need it for that heat.
Yeah, we sure do. Have you ever gotten yourself, hopefully you haven't gotten yourself burned on that one, have you?
No, not on that one. Pitot 19 has gotten me. Sometimes you turn the heaters down on Pitot 19 and they just are slow to respond. So you can think the temps are much lower than they are, and you touch it and you end up with burnt skin on your finger.
Oh boy. Yeah, well, I had to ask even more questions in that area, but maybe this is a good one to wrap up on here. Obviously, we talked a lot about sensors, a lot about engineering, about testing in the laboratory space, but obviously, as you mentioned, people are still needed to maintain these instruments, and quite frequently to be able to maintain the ice buildup, all those sorts of things. I think John asked this question, maybe was curious after seeing your de-icing video. So I mean, John asked, the video shows that the person is not anchored when going up to knock off the ice. Any scary moments when you have gone up there to try and de-ice yourself, trying to take care of these instruments?
So I would say my highest wind ever being up in that instrument ring is around 115 miles per hour. And I'd say it was probably similar in that video based on the way she was leaning into the wind. That's the big thing. So with wind, usually up here, if it's that high, it's not gusting. So that increasing wind isn't crazily catching you off guard. So you'd be surprised, but sustained at 100 miles per hour is not actually as bad as you might imagine, because you're able to lean into that wind. So that's a constant force against your body. You just have to counteract that force. It's not like, all of a sudden it's ramping up and suddenly forcing you against the side or anything like that. Usually the increases are such that you can kind of handle those increases. I've actually, in my experience, I've noticed that when we're down at lower speeds, like maybe 50 miles an hour sustained, and then we gust up to 75 in that range, that's actually scarier to be up there than around 100, because when it's up around 100, it never seems to increase too quickly at one point in time. But yeah, definitely you got to be careful. We don't tether ourselves in because it's actually, we've thought that it might actually be more dangerous, that you might get tangled up in your tether or something of that sorts. Personally, I've never felt too scared up there. It's that ring is pretty safe, and there's even another safety wire that's around the bottom. So it would actually be pretty tough to get blown out of there. But yeah, that's a pretty good question. I'm sure everyone's wondering that.
Yeah, I'm sure first-time observers are wondering that too, what the heck they've gotten themselves into. But I bet you, like a lot of observers, have sort of figured it out over time where your threshold is, and
hmm
yep,
I was
can
especially lucky. I started in the summer, so the summer is our season where we have usually our lowest winds, and I was able to kind of slowly ramp up from the summer all the way to the winter. So I kind of got a gradual increase in wind speeds. But yeah, I'd imagine it might be a little bit scarier if you were to start here in the winter and just immediately jump up to 100-mile-an-hour winds up there.
Oh, well, yes, I have some stories related to that, but that's for another program. Alrighty, well, thank you so much, Sam. I really appreciate all the time you spent pulling this together, and for everyone who joined this evening. Lots of thoughtful questions. Again, please reach out to research@mountwashington.org. Lots of questions we weren't able to get to tonight, so love to be able to respond to those. If you enjoyed tonight's free program, we would strongly encourage you to make a donation over at mountwashington.org. You can find a donate button up in the upper right-hand corner of that screen. And don't forget, any donation in any amount also makes you a member of the Mount Washington Observatory. So thank you, thank you, thank you. If you have thoughts about tonight's program or suggestions for future ones, please feel free to take some time to fill out a Google Form survey that'll show up in the Zoom window when we wrap up here, or in a follow-up email. And last but not least, don't forget to join us for our program next month. Tuesday, May 17th, we'll be joined by Vermont professor and state climatologist Leslie Ann Dupingy Giroux, who will be telling us all about the 4th National Climate Assessment, on which she was an author, and the impacts of climate change on the Northeastern United States. So don't forget to register for that program, or watch any of the other ones you may have missed over at mountwashington.org/SITM, and we will see you all again soon. Thanks so much. Have a great night, Sam. Thank you again. Thanks, all of you. We'll see you again soon. Take care.
Thank you.
Happy Big Wind Day. Night, night.